Hello everyone. Today I'm excited to demonstrate a new C# library called P2PNet, which simplifies the process of setting up peer-to-peer networks. In this demonstration, I'll show you how peer-to-peer net discovery works to seamlessly make peer connections, and I'll be using my desktop and laptop to represent peers. This video will primarily focus on the library's local discovery mechanism and the wide area network scanning feature, which leverages hardware capabilities in IP version 6 for serverless discovery. So first, let's look at our Visual Studio. As you can see here, we have a real basic, empty, brand new console application. Nothing's really going on here. I set up a publish directory on a network folder so my laptop can access it when it's published into a binary. And then I enabled include all content for self-extract just so we have a prettier standalone .exe. Nothing, none of the DLLs, publishing outside of it. Just so it looks nice and crisp. So let's go ahead and get started. First, we're going to add our NuGet package. Let's add P2PNet.widescan. Alright, let's get started on our code here. Let's get it all set up. We're going to be using P2PNet, using P2PNet.widescan, and then we're going to use a static instance of the P2PNet peer network. Alright, and that's about all we need to get started. I'm going to add read key. You could use while true or whatever you want to use just to keep the application open. Just for now, though, I'm going to use console.readKey just for simplicity's sake. The first thing we're going to want to do, and this goes for any peer-to-peer net application, whether it's a local area network-focused application or a wide area network-focused application, server-centric or client and server, you're going to load local addresses. And all this is going to do, it's kind of like an initialization in it. It's going to get the public-facing IP4 address, IPv6 address if it has one, kind of get the system information, network interfaces that are operational and running, just kind of get a feel for things and figure out how to get on the internet so it can facilitate the peer network. Next, we're going to begin accepting inbound peers. Now what this does right here is it tells the peer network, hey, let's open a designated channel where we will accept incoming connections to be further verified and filtered and, if trusted, enhanced communications with. And that's all this really does, really. Next, we're going to boot discovery channels. And all this does, this is more of a local area network-centric function. It basically just opens some local unicast/multicast channels and broadcasts the little sliver of information that would tell in your recipients, hey, we're over here, come find us, this is where we're at. And then further basically tells the network, hey, here's where I am, connect to me. Now this is really all we need for a very basic local area network with discovery. So let's go ahead and build this. Going to open this up. I'll explain the task manager here in a little bit, and we're going to publish it on that network folder. Give it a second. There we go. I'm going to go ahead and give my laptop a head start. Unfortunately, I don't have it set up to where my laptop screen can show in the video. I apologize for that. Maybe in the future I'll have that changed, but for now, just assume that it is booting up, and it is booted up on my laptop. I'm going to go ahead and open it on the desktop now. And this is about what is showing on the desktop. And here we go. We have successfully opened channel with new peer. This is basically the desktop finding the laptop, and here they are sending messages back and forth. Here they are again sending messages back and forth. And you're basically seeing the same thing on both screens between my laptop and my desktop. The primary differences being the addresses. Everything else looks pretty much identical. And that's about how easy it is to set up peer discovery on a local area network. Let me go ahead and close that out on my desktop. So let's go ahead and shift to the wide area network feature I was mentioning, the wide scan. Go ahead and erase these two. Like I said, we need to keep our load local addresses for the peer-to-peer net library. We're going to first, we need to tell the wide scan, hey, what piece of hardware are we going to use? Because essentially all that's being done is vast quantities of IPv6 addresses are going to be generated, like a vast quantity. And then as those are being generated on a parallel thread, basically, they're going to be processed by a consumer that is going to send out vast quantities of packets to each address. Similar to the local area network, it's going to have that sliver of information in each packet, but we're going to do it on the IPv6 protocol, which will basically enable real serverless peer-to-peer connectivity. So let's go ahead and tell the wide-scan feature that we want to do this on our GPU. You could do it on an accelerator, like a GPU accelerator or your CPU. I would personally advise against doing it on the CPU because GPUs and GPU accelerators are just more catered. They're more optimized for this kind of work. So let's go ahead and tell the wide scan feature we want to cap it at 2 gigabytes. Now let me explain what this is doing. As I said, it's mass generating IPv6 addresses, and this will eat up your memory pretty quick. Even if you got a lot of memory, you walk away and you come back and like 3 gigabytes of memory is just gone. You can see it in your task manager. That's why I have task manager open. I'm going to demonstrate how quickly it can creep up. So we want to cap it. Say, hey, no more than 2 gigabytes worth of IPv6 addresses, and then let the other workers kind of catch up and send the information out. Next, we're going to add the address prefix. Now, this is basically a 4-segment prefix. So after I put this in, alpha 822 430, 430, whoops. So an IPv6 address is 8 segments. So we're not generating all 8 segments. What we're doing is we're giving it a 4-segment prefix, and then the hardware is going to generate 0000, 0001, 0002, etc., forever, really fast. Now, the reason we are not doing all 8 segments is that would just be kind of a waste of time and resources, realistically. What you can do, and this is a very useful little tip, the prefixes that are registered by ISPs, like let's say AT&T, for example, are publicly available information. There are directories that you can find that will tell you what these prefixes are being registered to. You can find like Cox Business Network, or Cox Business Internet, whatever it is, AT&T, all the other ones that register IPv6 addresses. You can use that publicly available information and leverage it to sort of narrow in on more likely spots or likely connected peers. Also, it tends to be geographically linked, I believe. IPv6 addresses, when the prefixes are registered by companies and organizations, they do tend to be geographic. So you could sort of zero in on like American AT&T users, which are more likely to be like home internet connections, home internet routers and stuff. You know, people just on their computer, and you could connect that to like Australian. I don't know what ISP companies are in Australia, but you could sort of do the same thing, and you could sort of narrow it down so you're not just wasting time and resources of your servers or whatever systems you have doing this, to sort of broaden or heighten the chance of finding other peers, servers, without using any centralized server. And that's really all we need to get started. We need to set the hardware mode and then add an address prefix. The maximum memory allocation, that's optional. It defaults to no limit for this video up at 2 gigabytes, but this is about all we need to get started. So let's go ahead and do widescan.startScan. And you're going to see my poor little workstation here is about to take an absolute beating. Yeah, my GPU is already getting revved up to 80-90%. Yeah, my CPU, that was about what it was. It's going up to 60, fluctuating between 55 and 60. Network is looking about as solid, is fluctuating between 32 and 40 kilobytes per second, which, given, I guess, the size of the information being broadcasted in these packets, I guess that sounds about right. And you can see here it's sending out to the available network interfaces. It's sending the packet. So what it does here, sent packet out on this driver, and since there is no error, it sent 2 additional packets, just as a redundancy. So each address is getting sent 3 packets in total, and it's the same identical packet. And you see our memory is slowly creeping up here. 12.6, 12.7. Here in a few more seconds, it'll be 12.8. And I'll just keep climbing and climbing and climbing until at some point it's like, hey, let's let the consumer thread catch up before we start producing more. So here you can see it's taking a dip. GPU's down to 30%, 36%, but our Wi-Fi is just cranking it out. You can see our producer is sort of capping off right there, taking a break while the consumer sort of catches up a little bit. And here we go. So revving back up. Kind of see how that corresponds. And now we're already up to 15.6 gigabytes of memory, still climbing. God, it's got to be easily, well, we started at like 12 or 13, so it's easily like, I don't know, a couple of gigabytes by now. But thank you for watching. I hope this was informative, and I hope you appreciated this little demonstration here. And I hope to have this finished, a preliminary beta release by the end of this year or early next year. This is entirely open source. My GitHub, all the code is open source. I'm hoping to have it published on NuGet maybe next year, mid next year, early next year, somewhere around there. We'll see. And hopefully this can help facilitate your application needs and your networking ideas. And if you have any questions, don't hesitate to ask. And again, thank you for your time and thank you for watching.